Hello. We will go over this problem. Our goal here is to determine if the series with terms, the square root of n plus 1, minus the square root of n minus 1, divided by the square root of n square minus 1, for n going from 2 to infinity, converges or diverges. If we prove that the series converges, then we will try to compute its sum. Without any further ado, let us start studying the series. When you have this type of series, the first thing to do is analyze the term. We define the term as xn. For each n, xn equals the square root of n plus 1, minus the square root of n minus 1, divided by the square root of n square minus 1. At first glance, we easily see that the square root of n plus 1 is greater than that of n minus 1, for all n greater or equal to 2. So xn is non-negative, for all n greater or equal to 2. Then we will apply tests recommended for series with positive terms. One of the main tests we use when studying series is the ratio test. So we will start by applying the ratio test to the series. We define L as the limit when n goes to infinity of the fraction, xn plus 1 divided by xn. Thus, L is the limit as n goes to infinity of the fraction with the numerator, the square root of n plus 2, minus the square root of n, divided by the square root of n plus 1 square minus 1, and denominator, the square root of n plus 1, minus the square root of n minus 1, divided by the square root of n square minus 1. When simplifying the previous expression, we have L equals the limit as n goes to infinity of the fraction, the square root of n plus 2, minus the square root of n, divided by the square root of n plus 1, minus the square root of n minus 1, times the fraction, the square root of n square minus 1, divided by the square root of n plus 1 square minus 1. This limit equals 1 because if we expand the numerator and denominator of this fraction, we will see that we have a difference of the square root of polynomials with leading coefficient 1, and of the same degree, 3. Consequently, the ratio test is inconclusive. Whenever this happens, you have to use a different strategy. This should force us to look deeply at the series term to see if we can come up with anything that will give us a clue on how to handle the series. Please do not forget to like the video and subscribe to our channel. Thanks to those who have already done so. Thanks. Clearly, we need to simplify the expression of xn. This will certainly help us. One can easily see that xn is also equal to the square root of n plus 1 divided by the square root of n square minus 1, minus the square root of n minus 1, divided by the square root of n square minus 1. So, we can rewrite xn as the square root of the fraction n plus 1 over n square minus 1, minus square root of n minus 1 over n square minus 1. Now, we expand the denominator using basic algebraic identities, and we obtain, xn equals, the square root of n plus 1 over n minus 1, time n plus 1, minus the square root of n minus 1, over n minus 1, times n plus 1. We simplify the common factor on both fractions and obtain, xn as 1 over the square root of n minus 1, minus 1 over the square root of n plus 1. This new format of the term of the series suggests that we should analyze the series as a telescoping series. Because its term can be expressed as a difference of two decreasing sequences, namely, 1 over the square root of n minus 1, and 1 over the square root of n plus 1. We shall then analyze the sequence of partial sums of the series. Note that, the sequence Sn is defined as the sum of the terms xk with k going from 2 to n. So, S2 equals x2 which is 1 minus 1 over square root of 3. And S3 equals x2, plus x3, which is 1 minus 1 over square root of 3, plus 1 over square root of 2, minus 1 over square root of 4. S4 is equal to x2, plus x3, plus x4. One can easily see that, there are terms with their opposites in the sum S4, namely, we have 1 over square root of 3, and negative 1 over square root of 3. We should cancel those terms and simplify S4. So we cancel those terms and obtain S4 as 1 plus 1 over square root of 2, minus 1 over square root of 4, minus 1 over square root of 5. Likewise, S5 have terms that can be cancelled. In fact, in S5, we should remove 1 over square root of 3, as well as 1 over square root of 4 and their opposite values. Similarly, in S6, we can cancel all terms except 1 and 1 over square root of 2, and the last two terms, namely, negative 1 over square root of 6, and negative 1 over square root of 7. Following the same procedure, one can easily prove by induction that in the expression of Sn, we can cancel all terms except 1 over square root of 2, negative 1 over square root of n, and negative 1 over square root of n plus 1. Therefore, Sn is equal to 1 plus 1 over square root of 2, minus 1 over square root of n, minus 1 over square root of n plus 1. We can now try to see if the limit as n goes to infinity of Sn exists. If this limit exists and it is finite, then we can conclude that the series converges. We know that the limit as n goes to infinity of 1 over square root of n is 0, the same is true for 1 over square root of n plus 1. Consequently, the limit as n goes to infinity of Sn is 1 plus 1 over square root of 2. So the series xn for n going from 2 to infinity converges because the sequence of its partial sums converges. And its sum is 1 plus 1 over square root of 2. We finally conclude that the series, the square root of n plus 1, minus the square root of n minus 1, divided by the square root of n square minus 1, for n going from 2 to infinity converges, and its sum equals 1 plus 1 over square root of 2. Please do not forget to like the video and subscribe to our channel. Thanks to those who have already done so. Thanks.